Hello and welcome to lecture 3 of CS 301 Systems 4 course. Today the topic for discussion is the concepts for concurrent programming. As we have gone through the previous videos, we have seen the difference between sequential, parallel and concurrent programs. So just to brief you on what is a sequential, concurrent and parallel program. A sequential program specifies sequential execution of a list of statements, and the execution of this program is called as a process. A concurrent program specifies two or more sequential programs that may be executed concurrently as parallel processes. For example, an airline reservation system that involves processing transactions from many terminals has a natural specification as a concurrent program, in which each terminal is controlled by its own sequential process. Even when processes are not executed simultaneously, it is often easier to structure a system as a collection of cooperating sequential processes rather than a single sequential program. A simple batch operating system can be viewed as three processes: a reader process, an executor process, and a printer process. The reader process reads cards from a card reader and places card images in an input buffer. The executor process reads card images from the input buffer, performs the specified computations, and stores the result in an output buffer. And the printer process retrieves line images from the output buffer and writes them to a printer. Hence, a concurrent program can be executed either by allowing processes to share one or more processors or by running each process on its own processor. The first approach is referred to as multiprogramming. It is supported by an operating system kernel that multiplexes the processes on the processors. The second approach is referred to as multiprocessing if the processors share a common memory, as in a multiprocessor, or as distributed processing if the processors are connected by a communications network. Hybrid approaches also exist. For example, processors in a distributed system are often multi-programmed. Concurrent programs. So a concurrent program consists of a collection of processes and shared objects. Each process is defined by a sequential program, and the shared object allows these programs to cooperate in accomplishing some task. The processes can be implemented by multiprogramming, where all share a single processor and are executed one at a time in an interleaved manner; by multiprocessing, where each is executed on its own processor in parallel with the others or by some combination of these approaches. The shared objects can be implemented in the shared memory or might simply be a computer communications network. An operating system manages execution of user tasks and controls processors and I/O devices that operate in parallel. Consequently, it has a natural specification as a concurrent program, with a separate process controlling each user task and hardware resource. And like any large system, an operating system must be organized so that it can be understood and modified. Structuring a system as a collection of processes and shared objects has proved to be an effective way to achieve this. So concurrent programs are useful whenever an application involves real or apparent parallelism, as the following examples show. So we have three examples here: computer systems, database systems, and computer networks. Computer systems, the availability of inexpensive microprocessors has made possible construction of computing systems that previously were not economically feasible. For example, such systems are being employed to control nuclear reactors, chemical plants, and aircrafts. The programs for these applications frequently are concurrent programs. Database systems. In order for a database system to service many terminals in a timely manner, transactions are processed concurrently. Implementing transactions so that they function correctly despite other transactions manipulating the database is a concurrent programming problem. Computer networks. Computer networks are becoming widespread. Such networks consist of collection of processors interconnected by communication lines. The protocols that enable processors to change data are concurrent programs. Communication and synchronization. All concurrent programs involve process interaction. This occurs for two main reasons. One, processes compete for exclusive access to shared resources such as physical device or data. Second, process communicate to exchange data. In both cases, it is necessary for the processes concerned to synchronize their execution either to avoid conflict when acquiring resources or to make contact when exchanging data. Processes can interact in one of two ways: through shared variables or by message passing from one another. Process interaction may be explicit within a program description, or it can occur implicitly when the program is executed. In particular, there is an implicit management of machine resources such as processor, power, and memory there that are needed to run a program. A simple example will illustrate these forms of synchronization. When shared variables are used, a process writes to a variable that is read by another process. When message passing is used, a process sends a message to another process. Both modes of communication involve a delay between the sending of a piece of information and its receipt. This delay has profound consequences because information obtained by a process can reflect a past state of the sender. Orchestrating cooperation among processes when the exact state of the system is unavailable can make designing a concurrent program difficult. Thus, communication between asynchronous processes cannot occur without synchronization. So, in order to cooperate, processes must communicate and synchronize. Communication allows one process to influence the execution of another and can be accomplished using shared variable or message passing. To communicate, one process sets the state of a shared object and the other will read it. This works only if the shared object is read after it has been written. Reading the object before it is written can return a meaningful but erroneous values. Interprocess communication. Basically, there are two types of interprocess communication: synchronous and asynchronous. Synchronous meaning that processes synchronize to exchange data. Asynchronous meaning that the process providing data may leave it for a receiving process without being delayed if the receiving process is unable to take the data immediately. The data is held temporarily in a communication buffer, or you can call it as a shared data structure, where several data items are buffered. These are made available to the receiving process in the order in which they arrive at the buffer. Communication between sender process and receiver process is often implemented using a shared buffer. The sender writes into the buffer, the receiver reads the buffer, and the receiver will read the buffer. So there are two forms of synchronization which are useful in concurrent programming: mutual exclusion and condition synchronization. So mutual exclusion is used to ensure that a partially written message is not read, and the access to the buffer by the sender and receiver is made mutually exclusive. Whereas in condition synchronization, if condition synchronization is used, we have to ensure that a message is not overwritten or read twice. The sender is prevented from writing into the buffer until the last message written has been read, and the receiver is prevented from reading the buffer until a new message has been written. Understanding the concurrent programs. So the program counter is a variable that denotes the next action to be executed by the process, and its value is changed as a result of executing the action. So let's see program counter as an example with respect to explicit or implicit variables. So we define the program state first. A program state associates a value with each variable, and the variables can be implicit variables or explicit variables. Explicit variables are defined by the programmer, and the program counter example that I mentioned is an example of an implicit variable. So program counter are variables which cannot be read or written in assignment statements. Shared communication channel is another example of implicit variable. Sending and receiving a message is usually the only way to exchange the value of implicit variables. Execution of concurrent programs. So how are the concurrent programs executed? So execution of concurrent program is defined in terms of atomic actions, each of which transforms the system from one state to another without appearing to pass through intermediate states. We can formalize program execution using a potentially infinite history. So this is the equation where we have S0 goes to S1 goes to S2 and so on up to Si to Si plus 1, where Si is called as a program state and alpha I is called as the atomic action. So alpha 1 is the atomic action that is going to be performed for translating the state from S0 to S1 and so on. So execution of each xi plus 1 in state Si can terminate in Si plus 1. State S0 need not be an initial state of a program. For a concurrent program, alpha 1, alpha 2, alpha 3 is the result of interleaving atomic actions from each of the component processes in the order these actions are executed. Finite histories correspond to terminating executions. The final state of a finite history must be one in which no atomic action can be executed. Even parallel executions can be modeled using interleavings of atomic actions. Importance of concurrent programs. Notational convenience and conceptual elegance in writing systems in which many events occur concurrently. For example, in operating systems, real-time systems, and database systems. Preserving the structure of concurrent algorithms. Third, speeding up program execution on genuine multiprocessing hardware such as network of microcomputers. Speeding up program execution even on uniprocessors. Concurrent programming allows lengthy I/O operations and the CPU operations to proceed in parallel. Advantages of concurrent programs. Reactive programming. User can interact with applications while tasks are running. Example, stopping the transfer of a big file in a web browser. Second, availability of services. Long-running tasks need not delay short-running ones. Example, a web browser can serve an entry page while at the same time process a complex query. Parallelism. Complex programs can make better use of multiple resources in new multi-core processor architecture, SMPs, LANs or WANs. Example, scientific engineering applications, simulations, games, etc. Controllability. Tasks acquiring certain preconditioned values can suspend and wait until the preconditions hold, and then the executions can be done in a transparent manner. Disadvantages of concurrent programs: safety, liveness, non-determinism, resource consumption. Safety: concurrent program should not corrupt consistent state of a program. Liveness: tasks should not suspend and indefinitely wait for each other, leading to deadlock situation. Non-determinism: what happens if a program has both concurrency and state together? This is very tricky. The same program can give different results from one execution to the next. This variability is called non-determinism. Internal non-determinism is not a problem if it is not observable from outside. Non-determinism, where a sequential program imposes a total ordering on the actions it specifies. A concurrent program imposes a partial ordering, which means that there is uncertainty over the precise order of occurrence of some events, and this property is referred to as non-determinism. A consequence of non-determinism is that when a concurrent program is executed repeatedly, it may take different execution paths, even when operating on the same input data. The classification of a program as deterministic or non-deterministic will depend on which of its actions are considered significant. Most programs are non-deterministic when viewed at a low enough level in their execution, but it is generally external behavior that dictates the overall classification. Resource consumption. A process wishing to use a shared resource, for example a printer, must first acquire the resource, that is, obtain permission to access it. When the resource is no longer required, it is released. That is, the process relinquishes its right of access. If a process is unable to acquire a resource, its execution is usually suspended until that resource is available. Resources should be administered so that no process is delayed unduly. A process may require access to one or more resources simultaneously, and those resources may be of the same or different types. The resources may be defined statically within the program or created and destroyed as the program executes. Also, some resources may be acquired for exclusive use by one process, while others may be shared if used in a particular way. For example, several processes may inspect a data item simultaneously, but only one process at a time may modify it. So threads can be expensive. Overhead of scheduling, context switching, and synchronization is a resource consumption problem. Concurrent programs can run slower than their sequential counterparts, even with multiple CPUs. Disadvantages of concurrent programs, in addition to the previous disadvantages, the first is deadlock. Deadlock: a process is said to be in a state of deadlock if it is waiting for an event that will not occur. So deadlock usually involves several processes and may lead to the termination of the program. A deadlock can occur when processes communicate. For example, two processes attempt to send messages to each other simultaneously and synchronously, but is a problem more frequently associated with resource management. In this context, there are four necessary conditions for a deadlock to coexist. Processes must claim exclusive access to resources. Processes must hold some resources while waiting for others. That is, acquire resources in a sequential fashion. Third, resources may not be removed from waiting processes. That is no preemption. A circular chain of processes exists in which each process holds one or more resources required by the next process in the chain. Starvation. Starvation is when a process is always denied a resource that it needs, resulting in the process never completing. So, starvation is also called as indefinite postponement or lockout. A process is said to be indefinitely postponed if it is delayed, awaiting an event that may not occur. And this situation can arise when resource requests are administered using an algorithm that makes no allowance for the waiting time of the processes involved in the system. Systematic techniques for avoiding the problem place competing processes in a priority order such that the longer a process waits, the higher is its priority becomes. Dealing with processes strictly in their delay order is a simpler solution that is applicable in many circumstances. Race condition. Race conditions are when two processes are sharing the same storage location, that is, it may be a variable, and the result of operations depend on the order in which they are ran. Overhead. There is additional processing overhead to coordinate the individual threads. This can mean for some problems a single thread is more efficient than multiple. And the last disadvantage is busy waiting. Busy waiting, regardless of the environment in which a concurrent program is executed, it is rarely acceptable for any of its processes to execute a loop awaiting a change of program state. This is known as busy waiting. The state variables involved constitute a spin lock. It is not in itself an error, but it wastes processor power, which in turn may lead to the violation of a performance requirement of the system. Ideally, the execution of the process concerned should be suspended and continued only when the condition for it to make progress is satisfied. Concurrent programs and concurrent system. A concurrent program is primarily a coherent unit of software. If two pieces of communicating software run concurrently, the result is a concurrent program when the two pieces form a conceptual whole. Otherwise, the situation is viewed as two programs communicating through an agreed protocol. The communicating programs do, however, constitute a concurrent system. That's all for this video, and in the next video we shall continue with the next topic. Thank you for watching.